Last class, we left off with the circle of pH, which if you've taken 3A or 1A with me, you may have seen before. Basically just a way of getting around between these different terms. So a couple of terms that we might see, concentration of H3O plus, we can turn that into pH using these two equations. We can turn it back with the other one. We can also get to the concentration of hydroxide using our Kw constant. And on the other side of the circle are POH, which we can convert to pH using our 14 equals pH plus POH equation. And we can also undo the log, that's the P part, the negative log. We can undo that to turn it back into concentration of hydroxide. So this might be a helpful tool if we're moving around with pH stuff. Obviously there's like a fastest way to get to some value, like if we've got hydroxide concentration. Yes, you can turn it into POH, then pH, then back into hydroxide concentration, but it would probably be faster to just go ahead and turn it into hydronium concentration immediately in one step. Testing some of our knowledge on what we learned last class, which was our review of 3A/1A, maybe 1A, acid and base concepts. As the pH of a solution increases, gets higher, number gets bigger, what happens to the acidity of the solution? Does it increase, decrease, or remain constant? B, it decreases. Low pH is more acidic. High pH is more basic, which is less acidic. In acid solutions, we have two possible sources of hydronium ions or protons in solution if we have an acid. We've got, of course, the ionization of the acid itself. That's usually going to be dominant. We also have the autoionization of water from our Kw. The autoionization of water can be ignored in all but extremely dilute acid solutions. There is, in my mind, a famous trick problem that takes advantage of this fact, where you basically just have a dilute, strong acid in solution. You ask, okay, well, what's the pH of this solution? And if you don't remember that water autoionizes, then you get a pH of like 8 for an acid solution. And your brain says, oh, that's wrong, but I did the thing right. And then you might end up getting the wrong answer. Maybe I'll give one of those examples later. Our strong acids, by definition, ionize completely in water, and so the concentration of H plus is equal to the concentration of the strong acid. This assumes that it's monoprotic and not diprotic. So if we have a 0.10 molar HCl solution, HCl completely dissociates into H plus and Cl minus. Those H pluses, of course, go on to form H3O plus. Since it's complete dissociation, we can use the 1-to-1 ratio. That's why it's a concentration of 0.10 molar for the H plus. So if we wanted to be really diligent about showing our work, we could do something like that. We get a concentration of H plus that's 0.1 molar. We take the negative log of that, and we get a pH of 1. We also have weak acids. And you might have been thinking, wow, this is all not too bad. This is pretty easy stuff. We're bringing ice tables back for weak acids. It's still not too bad. It's the same ice tables that we've been doing before. Arguably, it's easier because we're dealing with pretty much a set standard dissociation equation. So calculating the hydronium concentration of a weak acid requires solving an equilibrium problem because we have those double-headed arrows. So using a generic HA that's in equilibrium with the A minus and the H plus. Since we have equilibrium arrows, there's going to become a point when this is in solution that will establish equal rates in the forward and reverse directions. And so we can solve it like an equilibrium problem. That means using ice tables. We are going to estimate the initial H3O plus concentration as 0, since typically we're going to be dealing with much more acid than we have the contribution of water's autoionization. So we're just going to ignore the autoionization of water for the most part. So if we're starting with a 0.10 molar solution of some generic weak acid, our weak acid is on the left side, it's a reactant. So we're going to be losing some amount of that. And we've got a 1-to-1 ratio to our other two chemicals here, our two products. So those are going to be gaining whatever we lose of our reactant. So that's why we have negative x plus x plus x. And so we can come up with these equilibrium values. I think this is, it's not the same. Okay, well, we'll just go ahead and solve one. All right, so we want to find the H3O plus concentration of a 0.250 molar hydrofluoric acid solution. We're given the Ka. If you were not given the Ka, like on a homework problem, then you should go look it up in a table or Google it. So our dissociation equation, I'm going to just go ahead and write it in as HF because it's the same as writing in HA, maybe a little faster. Right, so that's this is our balanced equation. And our equilibrium expression for this is our Ka. Why did I write KQ? Our Ka. There we go. And Ka is going to be the concentration of H plus times the concentration of F minus over the concentration of HF. So this is like the equilibrium constant when we were dealing with chemical equilibrium stuff before. We treat it exactly the same. The only difference is that we're using acids instead of like gases. And we set up an ice table. So we've got our HF, our H plus, our F minus. Initially, when our acid is introduced, we'll have 1/4 molar concentration. We're going to have approximately 0 H plus and 0 F minus. And then the change, we're going to lose 1 equivalent of HF because the coefficient on HF is 1. And we're going to gain 1 equivalent, or 1x, of both of our products. So our equilibrium values are as shown, 0.25 molar minus X, X, and X. And we can plug these in to our Ka. Let's plug everything in. 3.5 times 10 to the minus 4 equals X times X, which will become X squared, over 0.250 molar minus X. We can run this problem as written, or there's a way we can make it a little easier for ourselves. Who remembers what that easier step is? Yeah, we take out the X, but specifically we take out the minus X. We can't remove the X's on the top, just the X on the bottom. So we're going to try the X is small approximation. And since we don't really have that many terms, that makes this into a relatively simple problem. We'll rearrange, moving our molarity to the other side so that it's multiplied by our Ka. And on the other side, we've got X squared. To undo the squared, of course, square root, both sides. So what we're left with is X equals the square root of the concentration of the acid times Ka. The value that this gives is 0.0094. And since our concentration of H plus is just X, that means our concentration of H plus be 0.0094 molar. And that's what we were supposed to get. Questions about doing that? The other thing that we were supposed to do, if you remember, there's only specific circumstances where the X is small works, and that's, we can check that by taking the X value that we calculate here, divide that by our molar concentration, I think. My brain is not yet operational 100%. If we do that, we get 3.7%. That's under our 5% threshold. So there's our check that I put in there. All right, if we want to find the pH of a weak acid solution, we can also do that. It's very similar to what we were just doing. So again, we're going to do an ice table. I'm going to use the generic HA, H plus, A minus, because I'm a little lazy and I don't want to write in HC2H3O2 for HA. Our equilibrium equation would be this. Not using the generic this time. So notice we've got one reactant, we've got two products. In the problem, we're starting with an amount of our reactant. That'll go into the I spot for HA. So this has the same form as the problem that we were doing before. That's part of why I made the argument earlier that these are easier ice tables or easier problems to solve than the equilibrium stuff we were doing before. When the reaction proceeds, because we have reactant, our reaction is going to initially move in the forward direction, thanks to Le Chatelier's principle. Also, we don't have any product, so it can't move in the opposite direction. So we're going to move in the forward direction initially, so we're going to have minus X for our reactant. We're going to gain product as we move towards equilibrium. So our initial concentration of acetic acid minus X, and for H plus and A minus, just X. Again, we can write out our Ka, keep writing Kq. X over X kind of looks like a face. That might be how you feel. And completing our equation, we end up with this. So our Ka here looks eerily similar to what we had before. Right? All that's changed is a couple of numbers. The X's are in the same spots, just the numbers that are a little bit different. There's a pattern. Again, let's try the X is small approximation, because we don't really want to do quadratic formula stuff anyway. So we'll rearrange. We get 0.0150 molar times the Ka. We're going to square root that to get rid of the X squared that we would get up here. So for X, we are getting 0.000519615. We can give that units of molar, I guess. And we need to check and make sure that that works. So we'll take that X value divided by our initial concentration, times 100%. This is 3.5%. That's less than 5. So our approximation is valid. Or it's usable, at least. We're not going to be off by a terrible amount. Okay, so this result, this X value, the 5.196 0.19 times 10 to the minus 4, this number. We're good there. We don't have to do the full quadratic. And since this number is the same as our equilibrium value for H plus, that means concentration of H plus at equilibrium equals 5.196 ... times 10 to the minus 4 molar. So we can do negative log of that number to get our pH. And our pH is 3.28. Questions or confusion about either of those problems? All right, let's try another one. Let's find the pH for this solution of nitrous acid. So it's a 0.01 molar nitrous acid solution. We're again trying to find pH. We're provided with a Ka, almost identical setup to the previous problem. The only thing that's changed is our Ka is 10 to the minus 4, our concentration is 10 to the minus 2. Those are pretty close to each other, so it's very likely that X is small isn't going to work. There's another clue that X is small approximation is not going to work. What is it? It's the header. When X is small, it doesn't work. So it's not going to work out this time. We, got to show you those circumstances as well, just so that we're not always doing the X is small approximation, because that can get you in trouble. So using the same ice table, the same idea, our initial concentration of our acid is 0.010 molar. Our H plus concentration is 0. Technically it's not 0, but it's so small it doesn't make a difference. And our A minus is also 0. We're just starting with the intact acid. We haven't dissolved it yet. Our change values are the same as they've been, because it's the same type of equation. All right, so it's negative X for acid. It's positive X for both our protons, or our hydronium ions, and for our anion. So there's our full ice table. I even put in borders. So setting up our Ka is products over reactants. So we're going to have an identical Ka. H plus times A minus over the acid itself. So that means we have X squared on top, since concentration of HA and the concentration of A minus are both X. So just combine those. And then we're plugging in our equilibrium value for HA. on the bottom. If we plug in a Ka value, then we've got this. If we try our x is small approximation, we get that x is equal to 0.002. I'm just showing you that the x is small approximation is invalid here. So that concentration, or that x value divided by 0.01, times 100%, we get a value of about, sorry, it's 21%. We get a value of about 21%. That's bigger than our 5% that we're allowed to be able to do the x is small approximation. So it is actually invalid. I'm not just saying that. So what we get to do is rearrange a little bit more. So we're going to multiply both sides by our 0.01 minus x. And then we get to do 4.6 times 10 to the minus 4 times 0.01. That'll give us 4.6 times 10 to the minus 6 minus 4.6 times 10 to the minus 4x equals x squared, and then we can rearrange that to be 0 equals x squared plus our x and minus 4.6 times 10 to the minus 6. And this is where it becomes really handy to have my favorite calculator, my favorite scientific calculator, I should say, the TI-36X Pro. You just plug in the polysolver 1 and 4.6 times 10 to the minus 4 and negative 4.6 times 10 to the minus 6. Otherwise, you can use the quadratic formula yourself by hand. Which I've written into that top right corner. There's like a little song that you can sing to yourself to remember it, that for some reason the melody's stuck in my head. I'm not going to sing it for you, sorry. You can ask me offline. And our two solutions are this and a negative value. So we get these two solutions, a positive one, a negative one. The negative one's not going to work because we can't produce a negative amount of something that we didn't have already. Our H plus and our A minus values can't be negative. So we're choosing what I've labeled as X1 here. So down here in the bottom left corner, X, which is equal to the concentration of H plus, is the same value negative log of X will give us pH. So our pH, 2.7 So obviously not quite as nice when our X is small approximation doesn't work out. It's the same as the other ice tables that we've been doing, though. Questions about that problem? All right, we can also find the equilibrium constant from pH. We are still going to be using an ice table here. So we're given a concentration of a weak acid solution and a pH, and we want to find Ka. Some things that would be helpful for us to have here is our generic equilibrium expression. You don't necessarily have to write it out if you can just pull up the Ka expression. So we do products over reactants. And it's the same Ka expression that we've seen before. Nothing new here. What is new is the information that we're putting into our ice table. Set up our ice table, cross lines, vertical lines are optional. We're given an initial value for our HA, and we're approximating our hydronium concentration is 0. We are going to have a 0 concentration for the anion. Our change values are going to be the same change values that we've been using. Since we're starting with only HA, our reaction is going to move to the right. We're going to be producing H plus and A minus. We're going to be using up HA. They all have coefficients of 1. That makes this nice and easy. So negative X plus X plus X. Our HA at equilibrium is going to be the combination of those two values. And our concentration of A minus is going to be X. However, we've been given a pH value for this problem, and so we can solve for the equilibrium value for H plus. And since at equilibrium we're going to have 0 plus x, that means that whatever we get here is x. So we've got x. We can solve for x from pH. Since our concentration of H plus is equal to 10 to the minus pH. So 10 to the minus 3.25, 5.6, and some other stuff times 10 to the minus 4. So this number, this 5.6 and change, times 10 to the minus 4 molar, this is our x value. So if we plug in things for our Ka expression, Ka equals x for H plus times x for A minus over 0.175 minus x that means we've got 3.16, 1, 2, 3, 4, 5, 6, 7 times 10 to the minus 7 over 0.17 44 dot dot dot. And or if you did it in one step, .81 times 10 to the minus 6, I think is what I counted. Somewhere in that ballpark. So we didn't have to do quadratic stuff. This was our easier ice table. Since we had two values, we could figure out what our x is. Questions about any of that?
Where did the 3.16 come from?
That's x times x, or x squared.
Okay.
Assuming that I didn't do it wrong. Nope, looks like I did it correctly. You can also plug it in one step, which would arguably be better. All right, the initial concentration and Ka of a few weak acids, HA, are listed. For which of these is the Ka's small approximation least likely to work in finding the pH? The correct answer here is C. We've got a small concentration to start with, and we've got a relatively large Ka. we're most likely to be able to use our x is small approximation for B, because we've got several orders of magnitude difference between our Ka and our concentration of Ha. Which of these solutions is most acidic? That is, which one has the lowest pH? Think about what kind of acid HCl is, what kind of acid HF is. What kind of acid is HCl? Is it strong or weak? It's strong. What kind of acid is HF? HF is weak. So we've got a strong acid and a weak acid at the same concentration of the acid. The strong acid is going to be stronger. So it's definitely not B. So then the question is, if we double the concentration of our weak acid, is that going to be more than the concentration of our strong acid? Any guesses? It is not. So our strong acid is going to be stronger here. Ka is too small. For the concentration difference. So even though we doubled the concentration of our weak acid, it's still not even going to half dissociate. It's going to be much less than half dissociation, like 100th or 1,000th of it is going to dissociate, and so our concentration is going to be much lower. You can go back and find the Ka value and solve the ICE table for it if you wanted to. See that for yourself. Another new term, percent ionization of a weak acid. We can calculate percent ionization. It's the concentration of H3O plus at equilibrium divided by the initial concentration of the weak acid multiplied by 100% to get it into percent units. All right, let's find the percent ionization of a 0.25 molar acetic acid solution. We are looking for H plus at equilibrium. We're going to divide that by our initial concentration of the acid, multiply that by 100% to get our percent ionization. We already have our initial concentration of the weak acid, so we need to find our equilibrium concentration of H plus. That means an ICE table. since we have a monoprotic weak acid, it's the exact same Ka expression that we saw before, that we've been seeing. And our ice table is also going to look eerily familiar. Right, our initial concentration of HA that's given to us, our concentration of H plus is approximately 0. Our change values are minus x, plus x, plus x. And so our equilibrium values look awfully similar. All that's changed between the other ice tables that we've done before is this 0.250. Otherwise, it's exactly the same. So plugging in our Ka, simplifying our concentration of H plus and concentration of A minus to x squared, and dividing by our concentration of HA. Let's try the x is small approximation. It can save us a lot of time here. So the slash in there showing our x is small. We rearrange 0.250 times our Ka equals x squared. To get rid of the x squared, to make it just x, square root both sides. We have once again, thanks to our x is small approximation, ended up with our initial concentration times our Ka value under the square root. Part of why I've been pointing out that it's the same thing every single time, once you kind of get the hang of doing these, you can kind of just skip to the x is small approximation part, if you feel confident doing that. So x is 0.00212. Our initial concentration is 0.250, so we're a factor of 100 and some change. It's definitely less than 5%. So x is small is valid. So this number is our H plus concentration. So now we have our concentration of H plus at equilibrium. We can solve for our percent ionization. I'll do that in this bottom left corner. So 0.00212 ... molar over our initial concentration, 0.250 molar, multiply by 100%. We get a percent ionization of 0.849%. We having fun yet? I must be having fun because time is flying. It's crazy. Questions? It's ice tables all the way down, basically. All right, so some trends for weak acids. Our equilibrium H3O plus concentration of a weak acid increases with increasing initial concentration of a weak acid. However, the percent ionization of a weak acid decreases with increasing concentration of acid. So looking at two different situations for nitrous acid, a weak acid, 0.20 molar and 2.5 molar. We've got our calculated H3O plus concentrations and our percent ionization values shown there. Any ideas why that concentration, or that percent rather, is going down? We guess that our denominator is increasing. Our Ka expression is concentration H plus, concentration A minus. Over concentration HA. So part of the way that I was thinking of this is our A plus or our A minus term is in here, but it's not being factored into our ionization percent. That's one factor that we're losing out on, as well as our concentration of HNO2 is also increasing. So our denominator is increasing, and our A is not, or our H plus is not keeping up. So our concentration H plus increasing, but not by as much. Again, I think that's because of this concentration of A minus. We're just kind of losing that factor. If that's just completely confusing to you, don't worry about it. I don't think it's that important anyway. That being said, which of these acid solutions has the greatest percent ionization? Thinking about that trend we just established. Yeah, it's going to be C. They're all the same acid. All of these are acetic acid. And percent ionization decreases with increasing initial concentration of the acid. If you got this question on the exam, or something like it, you could also just solve for the percent ionization for these. Just make up a Ka if one's not given to you. Make it small enough that your exasmall approximation works, or just don't worry about the exasmall approximation or whatever. And you could figure out the trend from that too. Alternatively, there's your trend to memorize. percent ionization decreases with increasing concentration of HA. So that's all been fun, but you've been sitting there asking yourself, what if we made it harder? And boy, have I got an answer for you. This is what it might look like if we made it harder. So sometimes you'll get mixtures of acids. We can calculate the pH of a mixture of acids. It can be complicated. However, we can neglect, read ignore. We can ignore the weaker acid if we've got two acids and just focus on the stronger one, especially if we have a strong acid and a weak acid. So let's consider a mixture of hydrochloric acid and formic acid. Formic acid, HCO or HCHO2, is a weak acid. We have three, count them, three sources of H+ ions. We have the strong acid, the weak acid, formic acid, and the autoionization of water, the weakest acid in this case. So looking at those equations, we pulled out our Kas. HCl plus H2O is going to form H3O plus and Cl minus, and that is a strong acid, so it completely dissociates. So whatever amount of acid that we put in, assuming it dissolves, is going to result in the formation of the same concentration of H+. Little cough there. So that H3O+ that's formed by the HCl is going to suppress formation of H3O+. Because we've got some initial, what we're considering initial H3O+, when we're doing our ice table for our formic acid. So rather than starting with no H3O+, we have some initial amount of H3O+. We still have none of the formate, the CHO2-. We can calculate an X value based on this ice table, and we would find that it's 1.8 times 10 to the minus 4, which is way smaller than 0.1. So that 0.00018 basically makes no difference. It's effectively not doing anything. It's the weak group member. So it's basically zero when compared to our 0.10 molar concentration that we started with. It's there in spirit, but that's all it's there for. Let's say, though, we have a mixture of two weak acids, because it's boring if we only have one acid to worry about. Again, we have three sources of H3O+. We can ignore the weaker acid and water when the Kas of the weak acids differ by more than a factor of several hundred. So if we've got something that's 10 to the minus 2, something that's 10 to the minus 5, that would be different by more than several hundred. So we're looking at a difference in the exponents of 3 or greater. And if the concentrations of the acids are similar, or the stronger acid concentration is greater. So let's say it's HCl and HF, HF being a weak acid. So if the concentration of our stronger, no, that doesn't work, because this is two weak acids. We'll do HF and HC2H3O2, because I'm pretty sure that's weaker than HF. I don't remember the Ks off the top of my head. Let's just assume that 0.1 works here. So if our concentration of HF is greater than or equal to the concentration of our weaker acid. This is kind of just hedging our bets. There's probably some cases where the contribution of our weaker acid is still not significant, even if our concentration of the stronger one is less. So this is just like the safest set of conditions. Let's see what that looks like in practice. We want to find the ClO minus concentration, the hypochlorite concentration of a mixture that's got our favorite bathtub dissolver, hydrofluoric acid, and something else. HF is a weak acid. We've got a Ka. We need to figure out how much H3O plus it's going to produce. So find our H plus from HF. That's our first step, which means, you guessed it, an ice table. I'm going to sprint through this ice table. Famous last words. Okay, so after doing our ice table and writing our Ka expression, notice that it looks the same as it's looked every single time we've done it before today. Do our X's small approximation and draw the rest of the owl. And our X is 0.01438 dot dot dot. If we check our X's small approximation, we get a value of 4.8%. So we're good. Kind of skipped some of the steps there because I think the dead horse has had enough. So this X value is our concentration of H plus from the hydrofluoric acid. We said earlier that we can ignore the contribution of our weaker acid if our Ka values, which we've got 10 to the minus 8 and 10 to the minus 4, are different by a factor of more than several hundred. Our exponents are different by more than 3. We've got a big gap. And our stronger acid, HF, has a higher concentration than our weaker acid, the hypochlorous acid. So that meets both of our checkboxes. Now we have to figure out our concentration of the hypochlorite ion, which means another ice table. I heard you like ice, so I put ice in ice, so you can ice while you're icing, or something like that. So our second ice table, we've got our initial concentration of hypochlorous acid, and we now have a concentration of H+. This is the contribution from our HF. Thank you, HF. We love having more complicated ice tables. We initially have no hypochlorite, ClO-. Since we have no ClO-, we cannot have this dissociation proceed in the opposite direction. It has to go in the forward direction. So our X values are, you guessed it, minus X plus X plus X. Which gives us these lovely equilibrium values. We're going to plug those in to our Ka expression. Fortunately, we've got a really small Ka value relative to our initial concentration of 0.1. We can use the X is small approximation. At least we can try it. So our Ka value, 10 to the minus 8. Equals 0.001438. Nope, the other direction, sorry. 0.1438 dot 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 times X. I evaluated the right side. Divide both sides and flip our left and right. And our X here is 2.0 times 10 to the, 2.02 times 10 to the minus 1, 2, 3, 4, 5, 6, 7 molar. I'm moderately certain I did that correct. Hey, look at that, I did it. Questions?
Weren't you supposed to write another 0 for the 0.1438?
I did 0.01438 divided by 0.1,
Yep.
which is the same as multiplying by 10. I just initially did it wrong. All right, if we have to guess, which of these solutions is going to be most acidic, that is, which has the lowest pH number? Is it 1 molar hydrochloric acid, 2 molar hydrofluoric acid, or a mix of hydrofluoric and hypochlorous acid?
It's still not pH.
It's still A. It's a strong acid. Oh, pH is 0, sorry. Very strong. And the hydrofluoric is going to be like, I don't know, 2, maybe? I'm just guessing. Okay, so that's acids. There's also fun to be had with bases. So let's talk about it. Our strong bases are ones that completely dissociate in solution. So our hydroxide concentration is equal to the concentration of the base. Or 2 times or 3 times if dibasic or tribasic. So strontium hydroxide is dibasic. It's got 2 hydroxides on it. Those will both pop off in solution. So it's not going to be the same as the concentration. It'll be double the concentration for the hydroxide. Those are some of our strong bases. Generally, things that have an OH in them and are ionic are strong bases. That and are ionic caveat's important because alcohols also exist and they have an OH. Right, so that's CH3OH is methanol. It's an alcohol. It's not a strong base. So ionic plus having OH groups is our general equation for it's probably a strong base. So strong bases include our 1A metal hydroxides, lithium hydroxide, potassium hydroxide, sodium hydroxide, etc. Highly soluble in water. They are strong bases, and they can form concentrated base solutions, so relatively high molarity solutions, approaching and possibly even exceeding the 1 molar range. Our group 2A metal hydroxides are only slightly soluble. They're still strong bases. And these produce 2 moles of hydroxide per mole of base. So let's say that we've got 0.05 molar strontium hydroxide. We just use our 2-to-1 ratio, do a little Stoichs. And we get a 0.1 molar concentration of hydroxide, for example. If that's something that you feel comfortable doing in your head, I'm totally fine with that. You don't have to show me the work. Any burning questions before we wrap up for lecture 1 of today? Then we will pause there and start a new video in a few minutes.